This is video number 3 for section 5.3, log functions. All right, we're going to take this to the next step now and talk about log functions. A log function looks like this. It's got a y, or an f of x, an equals, then a log, then some sort of numerical base. In this case, it's a 2. And then the x part of the function is in the result position. Well, let's see if we can make a table for this function and a graph. Starting with the table, we've got x, we've got y. I think it's going to be helpful for me to think about what these two letters represent in this equation. We've already said the x is in the result position. What about the y? Well, a logarithm is equal to a power. The y is the f of x. That means the y is the power. X is the result, y is the power. That's helpful, I think, because normally when we fill out a table, we pick a bunch of x's, we stick them in, and then we calculate the y's. Well, if I want to do this by hand, which I do, it's going to be easier for me to go the other way around. It's going to be easier for me to choose some exponents, to choose some powers, and then think about what the result of using those powers would be. For example, if the power is -1, what's the result of taking 2 to the -1? 2 to the -1 is equal to 1/2. If the power is 0, what's the result of taking 2 to the 0? 2 to the 0 is 1. In a similar way, 2 to the 1 is 2. 2 squared is 4. 2 to the third is 8. All right, we've started with the powers and then we filled in the results. You can check any of these entries by simply plugging the x into the logarithm. For example, take this last one. Log base 2 of 8 would be my x. Well, what does that mean? It means what power do I put on top of a 2 in order to get 8? Well, it takes 3 2's. 2 times 2 times 2. So when the result part is 8, the power part is 3. That's what we've written down right here. We just started with the power because we figured that would be easier. Okay, we've got ourselves now a table of x, y values. Let's go ahead and plot the points and see what the graph looks like. So let's see, 1/2, comma, -1, 1, comma, 0, 2, comma, 1, 4, comma, 2, 8, comma, 3. I think that's enough to draw in a reasonably smooth curve. So we get something like this. Let's think about what happens at the ends. I think on the right, it's pretty obvious that this is just going to keep growing, kind of slow growth, but continue to grow in this direction. What about over here on the left? Is this going to slam into the x-axis somewhere? Is it going to go down? Well, this is where we can use one of those results from the last video. Remember we said that the x portion here, the result portion, will never ever be 0 or negative. It will only be positive. Well, if x can only be positive, it will never crash into the x-axis. What does that mean? It must mean that we've got an asymptote here. This thing is going to get really, really close, but it's never actually going to touch it, and so I show that with the asymptote. Take a look at the shape again. Hopefully it seems kind of familiar to you. It kind of looks like an exponential function shape. It's not exactly the same, but it has that similar curve. It's got an asymptote. Well, that is not a coincidence, and I want to show you that. Here's how I'm going to show you. Let me take that table that we had made earlier, and I'm going to flip around the x's and the y's. Now, when you take a table and you switch around the x's and y's, you are creating what we have called the inverse function. So this table represents the inverse function of the original function. If you look at this table carefully, you should recognize a familiar pattern. Take a look at the y values. 1/2, 1, 2, 4, 8. They're doubling. They're going times 2, times 2, times 2, etc. all the way down the table. That means this table is an exponential function. I think I can even write the equation down. The x's are going up by 1, which means that times 2 is the b, the base multiplier. I can also see the y-intercept right here in my table next to x equals 0. And so the equation y equals 1 times 2 to the x, that a times b to the x pattern, which simplifies to just y equals 2 to the x. Here's what we're saying. This function is the inverse function of the original. And the thing is, it always works out this way no matter the base. If I had started with log base 3 of x, this would be y equals 3 to the x. If I had started with log base 4, this would have been 4 to the x. Log functions and exponential functions are inverses of each other. Let's write down that result. We write if f of x equals log base b of x, then f inverse x equals b to the x, just the corresponding exponential function with the same base. That works the other way around as well. So if the original function is the simple exponential b to the x, guaranteed the inverse function is going to be log base b of x. By the way, that helps to explain why that graph had that familiar shape. If I go back to the graph and I add on to this picture the exponential function, y equals 2 to the x, I can just quickly mark these dots and then connect them in the usual way. And I've included the asymptote. Well, remember, when you have a function and its inverse, those two graphs are symmetrical across that diagonal line y equals x, and you can see that here clearly in the picture. So log functions and exponential functions are inverses of each other. Knowing this is very helpful. Let's take a look at one last example. This last example says, here's a function, f of x equals 6 to the x. It's just one of those simple exponential functions. And the question says, well, you write down the equation of f inverse x. Well, as long as you know these results, you don't have to do any work for these problems. If you see a simple exponential, 6 to the x, then automatically, according to our result here, the inverse function is just going to be the corresponding simple log function, log base 6 of x. That's it. There's no work to do. If you're wanting to maybe convince yourself that it really works, well, pick an x, let's say 2. Stick it into the original function. So f of 2 would be 6 to the 2, and I get as an answer to that 36. Okay, well, in the inverse function, all of this should be reversed, right? So if I go here and I plug in now 36, which gives me log base 6 of 36, the answer to that should be 2. Does it work? Of course it works, because log base 6 of 36 simply means what power do I put on top of a 6 to get 36, and that power is 2. These are definitely inverse functions then, because they reverse the x's and y's. In the exponential function, the input is the power and the output is the result. In the log function, it's reversed. The input is the result and the output